Have you ever wondered how an explosion so powerful it can flatten entire cities is triggered by the splitting of a single atom? Nuclear bombs have fascinated and horrified humanity for decades. In this video, we'll peel back the science and mechanics of these terrifying devices, from how a chain reaction starts to the mind-boggling stages of a nuclear explosion, and even the devastating aftereffects that linger for generations. You'll learn about the critical components, fission versus fusion, and why these bombs changed the course of history forever. If you've ever asked yourself how a mushroom cloud symbolizes power and devastation alike, you're in the right place. Stay tuned. This journey will enlighten, shock, and perhaps even make you question the path humanity has taken. 1. The basics of nuclear reactions. Nuclear reactions release energy by changing the nucleus of an atom, unlike chemical reactions which rearrange electrons. But what's the key to their immense power? The process starts with splitting atoms in fission. This occurs when a neutron strikes a heavy atom like uranium-235 or plutonium-239, breaking it into two smaller nuclei and releasing a tremendous amount of energy. The released neutrons then collide with more atoms, causing a chain reaction that rapidly multiplies. Ever wondered why fission can produce such a devastating effect, while chemical explosions pale in comparison? It's all about energy density. While chemical reactions rely on bonds between atoms, nuclear energy harnesses the immense forces binding an atom's core. 2. History of nuclear bomb development. The development of nuclear bombs began during World War II with the Manhattan Project, a top-secret endeavor that changed global power dynamics forever. When the bombs dropped on Hiroshima and Nagasaki in 1945, the world witnessed the destructive potential of nuclear weapons firsthand. How did a scientific race for dominance impact the modern geopolitical landscape? These two bombings not only ended the war, but also ushered in an arms race that spanned the Cold War. The journey from theoretical discovery to global deterrent reveals much about human ambition, scientific ingenuity, and the devastating consequences of wielding such power. 3. Nuclear fission. Breaking atoms apart. So, what exactly happens when a nucleus splits? Nuclear fission occurs when a heavy atom's nucleus absorbs a neutron, becoming unstable and breaking apart. This process releases a massive amount of energy and several more neutrons, triggering further fissions in a chain reaction. Achieving and maintaining this reaction requires reaching critical mass, the minimum amount of fissile material necessary to sustain the process. Have you ever wondered why achieving critical mass is a game changer for weaponry? It transforms a single, isolated reaction into an uncontrollable chain explosion capable of colossal destruction. Understanding this process is key to grasping the awesome power and dangers of fission-based weapons. 4. Components of a nuclear bomb. What makes a nuclear bomb so deadly? The answer lies in its sophisticated components. Fissile material, high explosives, a neutron initiator, and a tamper. Gun-type devices use conventional explosives to drive two masses of uranium together, achieving critical mass. Implosion-type bombs use precisely placed explosives to compress plutonium into a critical state. The tamper reflects neutrons back into the core, enhancing efficiency. Have you ever wondered why precision and synchronization are so vital in these weapons? Even slight imperfections could prevent a detonation or produce a mere fizzle. This deadly dance of physics and engineering ensures a weapon's destructive potential. 5. Initiation process. Setting off the reaction. To create a nuclear explosion, high explosives surrounding the fissile core must compress the material to reach critical mass. At the same moment, a neutron initiator introduces free neutrons to kickstart the fission chain reaction. Timing is everything. How can precision engineering affect the bomb's success? It's a deadly balancing act where milliseconds decide whether a bomb fizzles or unleashes catastrophic destruction. Precision ensures that all components activate in perfect harmony, creating an unstoppable chain reaction. This synchronization exemplifies how scientific precision can lead to unparalleled power, for better or worse. 6. The stages of a nuclear explosion. When a nuclear bomb detonates, energy is released instantaneously, creating a shockwave that travels at supersonic speeds. How does this wave of destruction unfold? First, The intense heat creates a fireball, incinerating everything within reach. Then, a blast wave demolishes buildings and infrastructure miles away. Finally, radiation spreads, causing long-term health hazards. The sheer complexity and scale of this process highlight the duality of nuclear technology. Immense energy released in seconds, yet impacts lasting for decades. Why do the stages differ from conventional bombs? It's the combination of thermal radiation, shock, and residual radiation that makes them uniquely devastating. 7. Fusion. The H-bomb, hydrogen bomb. While fission bombs split atoms, fusion bombs, or hydrogen bombs, combine them. How does this make them more powerful? A fission reaction acts as a trigger, compressing hydrogen isotopes to achieve fusion and release vast amounts of energy. This process mimics the sun's core and can be hundreds of times more powerful than fission alone. Did you know that fusion bombs rely on staged explosions? The fission explosion creates the temperature and pressure necessary for fusion to occur, amplifying the destructive yield. This innovation made the arms race even deadlier, demonstrating human ingenuity with profound and potentially catastrophic consequences. 8. Immediate and long-term effects of a nuclear explosion. The immediate effects of a nuclear explosion are horrifying. Intense heat vaporizes objects, shockwaves reduce structures to rubble, and radiation burns the skin. But what happens after the initial detonation? Fallout from radioactive particles contaminates soil, water, and air, posing health risks for decades. Why are these long-term effects just as feared as the blast itself? Radiation exposure can lead to cancers, birth defects, and ecological collapse. The balance of instant versus enduring damage underscores the enormous responsibility that accompanies nuclear technology. Understanding these effects reveals why nations worldwide continue to grapple with nuclear policy decisions. 9. Safety mechanisms and nuclear deterrence. How do we prevent catastrophic accidents with nuclear weapons? Advanced safety measures like coded locks, fail-safe systems, and authentication procedures are in place to avoid accidental detonations. However, the doctrine of nuclear deterrence, the idea that possessing nuclear weapons deters enemies from using theirs, dominates international relations. Can the risk of mutually assured destruction truly keep the peace? This fragile balance rests on rational actors and intricate geopolitical negotiations. While safety mechanisms reduce risk, the threat remains real, reminding us of the stakes in maintaining peace through deterrence. 10. Ethical considerations and global impacts. The ethical debate surrounding nuclear weapons has divided philosophers, scientists, and politicians for decades. Is it ethical to possess weapons of mass destruction as a deterrent? While some argue their existence prevents large-scale wars, others call for disarmament due to their devastating potential. Movements for nuclear disarmament have made strides, but challenges persist. What is the moral cost of maintaining these arsenals? As humanity grapples with this question, the focus shifts to balancing safety, security, and ethics in the nuclear age. The global community must tread carefully, aware of the lasting implications of nuclear power. 11. Future developments and challenges. Nuclear technology is constantly evolving. What new challenges does this pose? Advances like miniaturization and precision guidance could make nuclear weapons more usable, raising concerns about potential conflicts. Rogue states and terrorist groups seek nuclear capabilities, increasing the risk of proliferation. How can the international community address these challenges? Effective non-proliferation treaties, intelligence sharing, and diplomatic initiatives are essential to reducing nuclear risks. As new developments emerge, the global conversation must adapt, keeping pace with the ever-changing landscape of nuclear security. Nuclear weapons represent humanity's greatest power and gravest responsibility. From their terrifying inception during World War II to the present-day challenge of nuclear proliferation, understanding these devices is crucial for our future. Will we harness nuclear power for good or doom ourselves to repeat past mistakes? By studying their mechanisms, impacts, and ethical considerations, we can make informed choices about nuclear policy. Let's strive for peace, understanding, and a future where the destructive potential of these weapons is never unleashed. Thanks for watching. If you enjoyed uncovering the mysteries and exploring the unknown with us, give that like button a tap. It helps us keep asking the big questions. Got thoughts, theories, or insights burning in your mind? Share them in the comments. We're here for the curiosity and conversation. And if you want to keep the journey going, hit subscribe and ring the bell so you'd never miss an exploration. And as always, question everything.